Okay, now we talk about the quicksort's complexity analysis, okay, the time complexity analysis. Now, this is the most interesting part about quicksort algorithm, the time complexity analysis. We assume that all elements are distinct, okay? It makes life easier because if all elements are not distinct, the performance may not be as good. So, so what can be the worst case time of quicksort? So think about it. We have shown that example in the previous video, and we can show you that if the quicksort elements have to, we do this comparison if an element is less than the pivot or greater than the pivot. Now, if we have a completely sorted sequence, okay, like 1, 2, 3, 4, 5, and then this is the pivot, and then we are trying to check if this is less than the pivot or not. So this will not be, this is also not, this is also not, this is also not. So what is happening, so all the elements which are more than pivot, because all the elements here are more than pivot, this will go in one side, and the other side where all the elements are less than pivot, this side has no elements. You can see that this is 0 elements and this has all the elements. Now think about the other one, 5, 4, 3, 2, 1. Now you see this is the pivot and we are checking is all the elements less than equal to pivot or greater than pivot. Now you see all the elements are less than pivot because there is this array is reverse sorted. So again this part of the subarray will have all the elements and this part of the subarray will have 0 element at the end of the partition subroutine. So if the array is sorted or reverse sorted, okay, the both cases are not good for the partitioning because this will be a very unbalanced partition, okay. So that's why this is the worst case time of quicksort algorithm. Now you see, so this is we said that the worst case time is when the input is sorted or the input is reverse sorted. So then what happens, one side of each partition has no elements, okay. So you understood this is no elements, okay, no elements, and this is also no elements, this side has nothing because it's sorted or reverse sorted. And so if we write the recurrence relation, so what will happen, Tn, the time of running quicksort algorithm on n number of elements, the input size. So what will happen, so one side of the array will have 0 elements and the other side will have the remaining n minus 1 elements, without considering the pivot element. Now so assume that for housekeeping and for the partition, the cost is linear time. We said the partition and other housekeeping operations, okay. So this is the theta n linear time. So now so t0 is a constant time operation running on 0 input element. It's a constant time operation. It's a theta 1 and this is Tn minus 1 theta n. Now this theta 1 can be incorporated within this theta n because this is a larger order term. So when it's takes it into account, then what remains is Tn minus 1 and theta n. Now I have tried to show the recursion tree for this recursive relation. So you know that what happens for this recursive relation, Tn equal to, we have to write this one, the constant, as the root, and then the two the very varying parts, the recursive parts at the two children, left and right children. Now if we keep doing that, this is the next tree where Cn and this Tn minus 1, again if we put n minus 1 here, it will be T0 plus Tn minus 1 minus 1, so n minus 2 plus C of n minus 1 plus Cn, okay. So then this Cn minus 1 will have again two children, T0 and Tn minus 2. In that way it will grow. You see this side has no element. This is a highly skewed tree. It will form. See this, the height of the tree will be what? See every step it is decreasing by 1. This is n. This is n minus 1. This is n minus 2 and until it becomes 1 element, okay. So this height of this tree, h equal to n, you can easily find out the height of this tree is n. And at this side, this is actually always producing 1 element. So this is constant time theta 1, this is constant time theta 1, this is constant time theta 1, And what is the cost of this part? So this entire part will have how many elements? This will have, all the n elements. So this is actually c times k, and you sum for all n elements. Okay, so it's like k equal to 1, 2, 3, 4, 5 up to n. So this is equal to c k square, which is of the order of theta n square. So now this theta n square is summed up. You see this also theta 1 n times. You might remember I said that if it's just theta 1, theta 1, theta 1, 2, 3 times, that's still theta 1, constant time. But if theta 1 n times, or n can be sufficiently large, very large number, then this theta 1 will be summed up into theta n times theta 1, n times theta 1 is theta n. Okay, so now this theta, so this total summation of this tree is theta n plus theta n square. Okay, so this side, so now this if you sum them up, this becomes theta n square, which is the larger growth rate term. So so the total of this tree is actually theta of n square. Okay, so theta of n square. So this is the worst case running time of quicksort, and we show you that the worst case running time of quicksort is theta n square, which is not very encouraging considering the fact that we said quicksort is a wonderful algorithm. So now we will show you that the average case runtime of quicksort is very, very well defined. Now, what will be the average case? You can understand the average case is where the array is, the sub arrays, the sub, after the partition, the two sub arrays are very nicely balanced. Or, I mean, the best case, we never discuss the best case, but the best case should be where, the equal number of elements in both the sub arrays. So after we have shown the worst case analysis, where worst case means that the array is sorted or reverse sorted, that means one side of each partition has no elements, we talk a little bit about the best case analysis. Best case is in general is bogus. Okay, I have already told earlier, best case is bogus, means there is technically no meaning of a best case analysis. But here we are just trying to show best case to show you that the average case results of quicksort is also like the best case. So what is the best case of quicksort? So let's see, the best case will be that every time, as I said, the partition is perfectly split in the middle. Okay, so the splits the array in n by 2 and n by 2. I know that this n by 2 floor, n by 2 ceiling, just ignore those things for the sake of quicker analysis. So there will be Tn will be two subproblems of size n by 2. So that is 2Tn by 2 plus theta n, which is about partition and other subroutines, the housekeeping operations. So now you know this recursive relation. It's a merge sort recursive relation, and we find that 2Tn by 2 plus theta n, if we put in the Master's theorem, it is theta of n log n. Okay, so now suppose so the best case, this is the best case one, so which is theta of n log n, and the worst case was theta of n square. Okay, worst case. So worst case was theta of n square, and the best case is theta of n log n. Now there is suppose assume that the split is always 1/10 is to 9/10. 1/10 is to 9/10 is a very, very skewed split. Okay, so that means just assume that one side has one element and the remaining 9 elements are on the other side. Every time this kind of splits are performed by partition operations, so that you can see this is an extremely skewed split where 1/10 of the elements on one side and 9/10 on the other side. Now we are trying to show you that this is actually very similar to the best case, where half is this side, half is this side. Let's show it. So what will be the recursive relation? So Tn equal to T of n by 10 plus T of 9n by 10 plus theta of n. Okay, the housekeeping. So this is the recursive operation. We keep doing this on the Tn by 10 elements, and when we do the recursion tree, you know that Cn, which is the with the constant on the theta n, that will be the root, and the two children will be the two recursive operations, Tn by 10 and T9n by 10. Now, when we put 9n n by 10 here, so then it becomes Tn by 100, T9n by 100, and Cn by 10. Okay, so and when we put this one 9 by 10 here, this is 9n by 100, this is 9n by 81n by 100, and then 9 by 10 Cn. So in this way the tree grows, and then comes here. So we continue growth until we go to the single element. Now you see this side of the array is reducing every time 1 by 100 and 1 by 10, sorry, and this side is reducing every time by 9 by 10. So definitely this side will finish much faster. Okay, so this will have a smaller height. So suppose at this side it finishes, but this side will grow and finish much lower. Okay, it will have more height. So this is a more height. And now suppose we start summing up the nodes here. It's this level, it is Cn. What about this level? Cn by 10 plus 9 Cn by 10 Cn. So at this level, this is also, yeah, Cn. And in that way we keep adding them. There will be one height where this one becomes 1, so probably at some height like that up to here it will still remain Cn, but after that leaves will start dropping. Okay, so there will be actually nothing from this side and only contribution from this side. So how we calculate the height now? So the height, every time this is 1 by 10 decreasing, so the height of this tree in this side is like a log of n to the base 10, and height of this side is log of n to the base 10 by 9. Okay, so if we just write it, it will be, Tn is upper bounded by this side, because this is the more height, so they contribute more cost to the tree, and this contributes less cost. So this is the lower bound, this is the upper bound. Okay, so lower bound, and the upper bound. So it cannot be less than this, cannot be more than this, so it will stay in between the cost. So the upper bound will be how many times this, using this height. So this is Cn log of n to the base 10 by 9 plus theta n. Theta n is all the leaves in total will be theta n, and this is Tn is higher than this side, which is Cn log n. Okay, because this side height is Cn log n plus theta n. So I write Cn log n to the base 10 plus theta n. So this side is the Tn is less than this thing and greater than this thing. So Tn is actually bounded, upper bounded by some logarithmic function, and also lower bounded by another logarithmic function. So Tn in summary is actually theta n log n. Okay, Tn is equal to theta of n log n, we can say, in the high level analysis. So you can see, although this is a very, very skewed partition where only 1 by 10th of elements are in one side of the pivot, and 9 by 10 the all remaining elements, 90%, 10% and 90% elements on the other side, still this is as good as best case, n by 2, n by 2 in a half by half partition. So we can say that 10%, 90%, 10%, 90% split is asymptotically as good as a 50-50 or half-half partition. Okay, So this is the major, most important selling point of quicksort, and this is the reason everyone loves quicksort. But quicksort, when when you are doing on a large array, and if you have a tail recursive code like for the last few elements, you can easily deploy some other sort like insertion sort and stuff to make it quicker. If you keep doing a recursive algorithm for the tail recursive part, it is really costly. So the best idea is that when you do quicksort on a large array, keep doing that until like there are 10 or 20 elements, and then you deploy another algorithm like insertion sort, which will finish the tail much quicker than doing the quicksort till the end. I hope you understood quicksort. I have done the analysis of the worst case, and then I have shown you using with the tree, a recursive tree, how the growth, the analysis can be done. Then we have shown you the best case, just to give you an idea that quicksorts, the average case, a very skewed average case, also gives results as good as the best case. And then we have shown this 10%, 90% split with the tree and the different height analysis of the tree. This side of the tree will be finishing first, so the cost has to be more than this side. This side will be the finishing much later, so the cost is upper bounded by this side. So Tn is always more than this and less than this. So Tn on average is theta of n log n. Thank you so much.